Alright, this video begins with question 6, and questions 6 through 10 um, are about analyzing functions and matching those functions to their appropriate graphs. So question 6, or the function in question 6 is a polynomial, and we see that it has a 0 at 0, because if you put a 0 here, 0 squared is 0, and 0 times any of this is 0. So we have the function value is 0 at x equals 0, and the multiplicity is 2 because this x is raised to the second power. We also have a 0 at negative 2, and its multiplicity is 1 because the exponent here, not visible but not necessary to be visible, is 1. And then if you set this trinomial equal to 0 and try to solve it, you'll get negative values and, not negative, beg your pardon, you'll get complex values, and we cannot plot complex numbers in the real plane. So we have a 0 at 0 and a 0 at negative 2. There's a y-intercept at y equals 0, because when you put x into this function, that makes both of these terms 0, which gives us a function value or a y value of 0. The degree is odd, and the leading coefficient is negative. So now that means that the graph will turn up on the left end and down on the right. And you can see that the matching graph is graph D. Let's confirm that. Here are our polynomials. We see that the graphs for graph F, E, and C, and for that matter B, have too many zeros. The graphs A and D have zeros at 0 and 2 in the case of A, but negative 2 and 0 in the case of D. And we further confirm that this is graph D because it does turn up on the left end and down on the right. Now we move on to question 7, and we see that it has zeros at negative 3, negative 2, negative 1/2, and positive 1/2. Just stopping to think about that for a second, that means that the 3 of its zeros are going to be to the left of the y-axis. And so here they are listed. I've filled in the blanks, so to speak, with the zeros. Their multiplicities are all 1. So the graph will slice or cut through each of those zeros, each of those values. It will cut straight through because the multiplicity is 1. Now there's a y-intercept at negative 3/2, and that is easily identifiable as the constant term. If x was 0, all of these terms would disappear, and negative 3/2 would be what's left. So our y-intercept is negative 3/2. The degree of the function is even, and its leading coefficient is positive. So that means it's going to turn up at both ends. So it'll turn up at both ends, and it'll have zeros with a multiplicity of 1 at all of these spots. And we see that graph C is the graph that follows those, that meets those requirements. Negative 3, negative 2, negative 1/2, and positive 1/2, with a y-intercept of negative 3/2. 3/2 being 1.5, so this is negative 1.5. And it turns up at both ends, and so as our solutions tell us, the matching graph is graph C. Now when we get to question 8, we see our first rational function, and it's presented in its standard form and its factored form, and it's presented in the factored form, so it's easy for us to determine that the x-intercepts are at negative 3 and positive 1. If you put a negative 3 in for x here, you have negative 3 plus 3 is 0, and 0 times anything is 0. Negative 3 will not make the denominator 0, so we have we have an x-intercept there at negative 3, and we have one at 1 for the same reasons. The y-intercept is 3/2. We determined that by substituting 0 in for all the x's here. That means all those terms vanish, and negative 3 over negative 2 is positive 3 over 2, so 3/2 is the y-intercept. The function also has vertical asymptotes at negative 1 and positive 2, because the function can never have a value at x is negative 1 and x is positive 2. And because the degrees of both numerator and denominator are equal, there is a horizontal asymptote, and we determine that by dividing the leading coefficient of the numerator by the leading coefficient of the denominator. So that's 1 over 1, which is just, of course, 1. Now, you notice it says or. Or, this graph would have an oblique asymptote. So it's got to have one or the other, but it can't have both. But we have a horizontal at y equals 1, and so let's take a look and we see the matching graph is t. So let's take a look at our graphs, and this page is all polynomials. But back here we have rationals. And the asymptotes, the vertical asymptotes, were here we have negative 1 and positive 1. That's not where our asymptotes were. Here we have negative 2 and positive 2. The asymptotes for this function were, let's see, where were they? They were at negative 1 and positive 2. So, negative 1 and positive 2. This one's at negative 1 and positive 2. And there is a horizontal asymptote at 1. But the y-intercept is 3. So that tells us that we have to look for another function, and turns out, no surprise, that's graph t. Now, here's the horizontal asymptote at 1. The function does intersect that horizontal asymptote, but you might remember that a function's graph, a rational function's graph, can cross its horizontal asymptote or its oblique asymptote, but only at one point. And so that is the one point where the function intersects, and if you want to test it, you can estimate that this is, well, let's see, what, 1, 1/2, 1/4. Put 1/4 in and see if you get close to the value of a value of 1. Excuse me. So t is the graph that corresponds to this rational in question 8. Now, next we have another rational function, and it has vertical asymptotes at negative 1 and positive 1. Negative 1 and positive 1, and it's got an x-intercept at 2. 2 times 2 is 0. 0 plus anything is 0, and put 2 in the denominator, and you do have a value, so the function is defined at 2, and so we have an x-intercept at 2. And we have a y-intercept at 2 because, again, if you substitute 0 in for all these x's, all these terms disappear. You have negative 2 over negative 1, which simplifies to positive 1. So that's where the y-intercept is. And this function has an oblique or slant asymptote because the degree of the numerator is exactly 1 greater than the degree of the denominator. Now, if you wanted to divide this out to find out what that slant asymptote was, you would find that it's x minus 2, but that isn't necessary. You're not asked to do that. So we have, recapping, x-intercept at 2, y-intercept at 2, and vertical asymptotes at -1 and 1. So we come down here to graph U, and so we have an x-intercept at 2, a y-intercept at 2, and vertical asymptotes at -1 and 1. Now it's hugging the graph. The graph is much closer to those lines here on the right side than on the left, but that's the graph that has those asymptotes and those intercepts, and an oblique, a slant asymptote. Now, if you were to sketch the graph of this slant asymptote, you would find that it does cross the function over here. I can't recall where, but it does cross the function. It does intersect the function. I think it intersects it right here, and then so it's just above the graph here and below the graph here. And so, again, rational functions can intersect an oblique asymptote or a horizontal asymptote, and at only one point. So the graph that matches this function is graph U. Finally, graph 10 is another polynomial, and there's a lot going on with this one. This factor right here, x squared minus 4, is not factored here because I thought that that is just such an extremely rudimentary factorization. It's the difference of two squares. So I left it. That's the one factorization in these matching questions that I didn't do here, and I may or may not do that on the exam. I don't know. I don't remember what it's like. In any case, we have a polynomial with a 0 at -2, and its multiplicity is 1, and we have a 0 at -1, and that multiplicity is 2. So the graph is only going to bounce at -1, at x is -1. So we'll try to keep that in mind. Let's see, there's a 0 at 0, because we have an x here by itself. 0 here means this whole thing is 0. And its multiplicity is 1. Okay, multiplicity is 1, so the graph is going to slice straight through at 0. And let's see, we have a 0 at 3/2, because if we put 3/2 here, 3/2 minus 3/2 is 0. And its multiplicity is 1. So all the multiplicities of these zeros are 1, except for the 1 at -1. We'll have to look for that when we go look at the graphs. And finally down here, there's a 0 at +2. Again, this is because the x squared minus 4 is the difference of two squares, and it factors as x plus 2 times x minus 2. And the y-intercept is 0, because if you put a 0 in for x everywhere, you get a function value or a y value of 0. Degree is even, and the leading coefficient, which is just 1, is positive. And so we have a polynomial that, since it's even with a positive leading coefficient, it turns up at both ends. And so we take a look here at our polynomial graphs, and the only place where the graph bounces, I believe, was -1. This one tries to fool you because everything about this graph is the same as the one we just analyzed, but it is a mirror image of the actual answer, which is this graph. So the graph bounces at -1. This one, I guess, bounced at +1. So this graph has zeros at -2, +2, a y-intercept of 0, and a 0 with a multiplicity of 1 at 3/2, which is 1.5. And again, it bounces or just touches at -1. All right. So there you go. There's all 10 questions. If you have any questions for me, don't forget to text, email, or call me.